Welcome to this webinar we're hosting in collaboration with SAMA on automating data annotation with MicroModels. I'd like to welcome our guest speaker, Saul Miller, Director of Product Management at SAMA. Saul manages SAMA's data labeling products to ensure high-quality training data efficiently and reliably reaches their customers. Today, he's going to be presenting a talk on automating processes within the workflow to improve efficiency and guarantee high quality.
So by the end of the presentation today, I'm committed that you have a good understanding of SAMA, as well as the training data use cases that we see in the market, how we have applied our MicroModels approach to accelerating that annotation process using our own ML. We'll look at it in an academic context as well as an applied industry case study. And of course, more so than just talking about it, we'll look at it live in a demo. And as Nikita mentioned, happy to leave lots of time at the end of the presentation for any questions that you may have, and we can dig in more on any of the topics that I've covered. So thank you for being here with us. So before we can go any further, let me just introduce SAMA in general. And so SAMA is the training data platform trusted by the world's most ambitious organizations to develop accurate machine learning models. You can see the logos on the screen. We work with some of the world's largest and also most innovative companies, providing high quality AI training data that unlocks their initiatives. The SAMA training data platform is an ML data annotation platform built for scale and for high quality, really optimizing both ML and the human annotation process in order to provide that high quality annotation to our clients, and has robust API integration capabilities in terms of how integrating with our clients' pipelines on their asset side, as well as returning the training data back to them to kick off their training data cycles. We cover a variety of use cases, like you can see here on the screen, whether that's vector image annotation, like polygons and bounding boxes, video object tracking, semantic raster masks, as well as 3D LiDAR and point cloud annotation. We are quite a global company. And so particularly in terms of the data annotation market, we are vertically integrated. So we have primarily our product and R&D teams based in North America between San Francisco, Montreal, and Costa Rica. And then we also own and operate our own physical delivery centers in East Africa, with our largest facility in Nairobi and then 2 locations also in Uganda. This vertical integration of having everything in terms of product, tech, as well as the human annotators all under one roof gives us more control from beginning to end of our clients' data, security, as well as ensuring the high quality output. But in addition to that, it also helps us deliver on our social impact mission. It's important to remember that SAMA over 10 years ago was founded as a nonprofit organization. We've now since evolved to a for-profit organization. We're one of the only AI companies that can claim to be a certified B Corp. And in our history have positively impacted over 53,000 individuals with dignified work and livable wages. We actually just completed a 3-year randomized control trial with our partners at MIT evaluating the efficacy of SAMA's training data and employment process. So that's a little bit about SAMA and where we are coming from. But before we can talk about the role that machine learning can play in the training data process and the data annotation process, we need to talk about just training data and data annotation in general. And so the reality is that without training data, there are no AI. And so when we think about the AI value chain and what does it really take to bring a high performing AI model into production and have all the positive benefits that all of our clients are making these major investments in AI development, really has to think about the effort that goes into the training data component. And so that involves actually collecting the data and the assets, identifying the subset of it that's going to be used for annotation, analyzing it, actually doing the data labeling part, which is where we're going to focus today, and then handing that back off to our clients to actually do the model development, training, tuning, and deployment. And then based on those results in production, there may be a feedback loop that requires additional annotation, additional refinement, additional data to be collected, and so on. But as has been said many times in these forums, these conversations, right? garbage into the model is going to result in garbage out. And so we play a really key part in that value chain of making sure that the data annotation is of high quality. So when we talk about data annotation, the use cases, the applications, the industries are quite broad. Certainly that's what we see in our mix of clients and the work we're doing every day. Autonomous transportation is one that comes up often in this space, but not just about self-driving cars or autonomous delivery robots, but also in-cabin monitoring, driver alertness detection. Certainly in terms of e-commerce and retail, some of the more advanced digital buying experiences, certainly that have become more relevant during the COVID period and more shoppers staying at home, augmented reality, virtual reality, in communications, media, entertainment, smart hardware and software, sorting through and organizing your photos, all of those different applications. And then also increasingly we're seeing use cases in biotech, so analyzing medical imagery at scale, but not just biotech, but agrotech too. Looking at crops and identifying crop anomalies and disease detection are all common use cases that we see in the data annotation space. So within that data annotation space, there is a role that machine learning can play, and I'm happy to be presenting today on Sama's MicroModel approach to ML-assisted annotation. So first, let's talk about why machine learning. The reality is that annotating images, particularly at high quality, it's very time consuming. And the reality is that ML can help. So by automating tasks that can be learned by a machine, can positively influence the data annotation process. Humans are still very much required to verify and adjust the machine's output in terms of the high quality requirements and the high quality of the training data that's needed for these AI models to perform well in production. And this is not easy stuff. I like to say that this is stuff of science fiction, right? Of how machine learning and robots really can work in harmony with humans, combined with a human in the loop to have positive benefits. And so there is some existing thinking around this, particularly within instance segmentation use cases. There are ML methods to speed up the process that have been suggested. We're going to look at the Dexter model in particular a little bit later in the presentation. However, they're not typically tested in a production environment, both at scale as well as the quality bar that's needed in a training data production environment. And it's really important that the ML output needs to be easily edited by human annotators. So with MicroModels, what we're saying is that this is an architecture that allows us to expedite the labeling process by drawing on a library of models trained on specific use cases. These are smaller models that allow them to be more scalable, more robust, and therefore can be brought into production more quickly and with greater accuracy. So the MicroModels are in contrast to what you might also see in the market in terms of monolithic models, kind of the one model to rule them all. Typically, they require storing customer data, requires quite a long time to retrain across the entire new data sets and use cases, so in terms of their flexibility, and not very scalable in terms of their coverage. Whereas in contrast with the MicroModels, we don't rely on the storage or reusing of customer data. We have that library of models trained on these industry-specific use cases, which really enable that better accuracy because they're more targeted and more specific, and can therefore be more scalable and more robust as we piece them together to cover a variety of use cases. So let's think about this in the context of a task that you can see on my screen here, where we want to do object and scene segmentation using polygonal annotation, let's say around vehicles and pedestrians, bicyclists. With the MicroModels, it can be trained either way, either to support instance segmentation, where each individual instance is getting their own annotation, or semantic segmentation, where we might group together multiple objects that are all of the same class. And the way that our machine learning assisted annotation works is based on the Dexter model, where it receives from the user few clicks. So you can see here in the red dots on the screen, identifying the 4 extreme boundaries of an object of interest, like this vehicle, which can then derive a heat map from those user inputs at inference time, concatenate that heat map of the image of that focus, that hot zone, pass it through as an input through the Sama UNet and the Dexter model, And then the end result is a raster mask prediction of that instance. We're not done there yet. So from that raster mask, we then do a little bit more refinement to convert that raster mask back into a sparse polygon that's returned to the user in the interface as a predicted polygon. You can see some visual examples of those results here, where we have manual annotation of the vehicles, as well as the results of the few click annotation for the same images. You can see that they are providing a similar intersection over union. And we're also putting some special thought into making sure that the predicted polygons result in similar vertices to the hand-drawn ones. And also as a reference, I'll be happy to share a research paper that we published that was originally presented at CVPR, which really focuses on this approach of human-centric efficiency improvements in image annotation. It covers, it also highlights the content that I've shared so far, and but also goes a step further in terms of the observations, again, like we've been talking about with this relationship between the ML prediction and the human annotator. It can't be understated. And in our research, we actually see different results between just pure pre-labeling, which again, still results in a prediction for the user to modify and refine, versus using few click annotation, where the prediction is integrated into the annotation environment. And the human is actually part of co-creating that polygon in terms of the ownership and the familiarity with that polygon, actually resulting in more efficient annotations. So in a controlled A/B testing environment on vehicles, for example, what we saw and what we were able to observe and measure was predictably producing a 94 to 98% accuracy IOU of the model prediction versus the final polygon after human refinement. And also a huge increase in efficiency. So 2 to 4x more efficient in the annotation process of generating that. I think when I do the demo, it'll be immediately clear to you why that's the case. And that this is an iterative process that based on those human modifications of the predictions that gets fed back into the training data pipeline, retraining the model to then perform even better the next time around. And the end result for our clients and the business value here is really quicker time to market. That much more efficient annotation process results in shorter projects, more data returned quickly. And also, if we're able to increase the efficiency of this labor-intensive manual data annotation process, it also reduces the barrier to entry for more clients, more types of companies. The logos I showed on that first slide are quite large, quite powerful companies with large R&D budgets. But if we're able to democratize the data labeling just a little bit more, driving down cost and availability, then even more applications can start to take advantage of this really powerful technology. So A/B testing is one scenario. I want to spend just a few minutes talking about an applied case study that we see with one of our production projects as well. And so we'll focus just on an automotive case study. I've been using that throughout the presentation. And so I'm keeping the client anonymous for obvious reasons, but we're working with a tier 1 automotive supplier. And what they were asking us to do was a really highly complex workflow involving various camera data sets of that kind of polygonal annotation of the example I showed a few slides ago. This is a highly dynamic data set that has varying weather conditions, seasonal conditions. It's quite a large data set. And of course, as always with clients, right, there's a tight deadline and tight turnaround because they want to bring their model to production as soon as possible. So we were able to implement the ML assisted annotation to reduce time spent on that polygon drawing and increase annotation efficiency. And the end result was a 27% decrease in the overall project length with really high quality performance from the model at 96% plus IOU, including, because of the MicroModel approach, the ability to do smaller retraining loops as the data was evolving over the life cycle of the project to continue to stay highly performant in those evolving conditions. Okay, so now do what I think we've all been waiting for, which is let's look at it in the workspace itself. And what I'll highlight is both ML assisted polygon drawing as well as polygon editing. So let me just jump over into the Sama platform. I'll do a refresh here just to be safe. Okay, so let's look at an example image here. We're here in the Sama annotation platform. This is the workspace that our agents see every day. And let's just say that the nature of this task was to draw instance segmentation polygons around each of these vehicles. Well, first of all, like, oh, wow, right? Like this is, there are hundreds of vehicles in this image. You know, in a manual context, this may be something that may, you know, take a human all day to do high quality annotations, several hours, right? You can imagine. And that's because the manual annotation process, let me just zoom in on a specific vehicle, right? Would look like this, where you're clicking and drawing a polygon to go around this specific object. I'm not even doing a great high quality job here. So I'm sure any of our agents who do this all day, every day would be laughing at me in terms of the quality of this annotation, but you get an idea of what the manual annotation process can look like as I'm going around and trying to do a accurate polygon on this shape. So let's now take a look at what that can look like with machine-assisted annotations. I'm going to just delete that, and I'm going to switch from manual mode into ML polygon mode. And as you saw in the earlier presentations, the model works based on extreme points. So we have this crosshair tool where I can identify the extreme left, the extreme top, the extreme right boundary, and the extreme bottom. That again is going to create that heat map that's sent to the inference server. And voila, you can see it's returning a polygon prediction. Let me switch into editing mode that can then be further refined by the agent just to reach those high level of quality requirements that we know that our clients require. So huge time savings. Let me just tighten up the mirror there a little bit, right? Huge time savings over the manual approach. Let's look at another example over here. I'll do another kind of zoom in. I want to also demo for you. Hopefully I can create this well for you. The ML assisted polygon editing as well. Let me drop those 4 extreme points again. Of course, the demo gods got me. Let me stop work and start work again. Sorry about that. Hopefully that will just resolve and we'll be able to take a look at that second vehicle here. So again, I'm going to switch into smart polygon drawing mode. Do the extreme clicks. And so what you saw before, you can see that, I mean, I did it on purpose. I placed the extreme point here as opposed to actually on the extreme right of the object here for the vehicle. But in addition to the manual editing that you saw me do before, the model also accepts more than just 4 extreme points in order to produce an even more accurate prediction. So I'm now using that smart edit mode where I've now dropped a 5th user input point. You can see the model repredicted itself to now capture that edge. I'll see if I can also do it over here and get just slightly better results. So we can see that when the model struggles with an oblong shape or something like that, then we can also add a few more inference points to help result in a more accurate prediction and then refine it further from there using the manual tools. So those are the detailed views that I wanted to cover, but let's just like get an appreciation of what this can now look like if you were trying to efficiently annotate. I'm not going to quite go to the same level of quality, but let's just do a few back-to-back replicating those results. Again, doing those 4 extreme points. Come over here to this SUV. Let me get that right boundary a little bit more accurately. I'm just going quickly here. So really impressive every time. Let me zoom out a little bit. We can kind of appreciate. I'll turn up the opacity just so we can appreciate the quality of those initial predictions. Again, what we observe consistently with this micromodel approach is somewhere to 96 to 98% accuracy between the model prediction and the end result after the agent makes any final tweaks to still ensure high quality. I'm just pausing there. Okay. So that is the demo of both ML-assisted polygon editing, annotation and ML-assisted polygon editing. And I'll just come back to the presentation for any questions. I think I must have talked a little fast. We're doing it ahead of time, so that's good news. It means that we can spend time on questions and things that matter most to you.
Thank you so much, Saul, for a great presentation and demo as well. Thanks for doing that live for us. I know it's never easy. So we do have quite a few questions. So the first one came in from Lumi, who I think I recognized from our event last week. So hello again. So Lumi has asked, how long is the time between the model deployment and optimization of the data?
It's a great question. So there's both. I think there's two different ways to answer that question. The first is thinking about our clients and their use cases. And so in that context, we have a little bit less visibility to that. But typically a client will engage us in terms of the training data we're providing to them, maybe for a concrete scope in terms of a specific volume, reach a specific milestone. And then we do often see that that same client come back and engage with us after they have some results in production. Maybe instead of doing annotations from scratch this time, now they're providing some pre-annotations from their model that we may be refining. And I didn't actually demo it, but that ML-assisted polygon editing is actually compatible with pre-annotations as well. There's no dependency there that polygon needed to be generated from the ML prediction to begin with. We could have started with a polygon that a client's model actually predicted. They provided to us as a default answer, and then we use the ML for the editing on top of that. And so those timelines definitely vary. In terms of our own model deployment and optimization, because again, in this context where we're deploying ML in the data annotation process, we're basically having the same experience that our clients are having with their production models. We're basically running our production models within the data annotation process. And that is a continuous monitoring approach. And so we've instrumented the platform to be consistently monitoring the IOU performance the intersectional reunion, the IOU performance of the model prediction against the final result after the agent may make any final tweaks or refinement. And so with that instrumentation, we can be very aware of when there is any drop off in model performance, maybe the data set evolves, and trigger that retraining pipeline. The trick there is you don't want to overcorrect. As much as the model retraining process with the micromodels can be really quick and nimble, it does incur a cost. And so we typically like to see, I would say, about a week of data if it's consistently going in a trend, and then we'd kick off a retraining process within ours in terms of optimizing and feeding it back into the annotation process. So hopefully that answered your question.
Okay, great. We have a question here from Ali who says, thanks for sharing this cool work. As you've been working exclusively in this direction, how do you see the future market of data annotation in general and MAA in particular? And then a second follow-up question, what should be the level of agent using these tools?
Yeah, absolutely. So, I mean, I think that to me, this machine-assisted annotation, this is the future of the data annotation market, right? That the opportunity is there, that there is a positive role that machine learning can play in the human in the loop data annotation process to help increase efficiency or also optimize quality. What we have observed in our experience is that we do have to be selective about those opportunities, right? And like I said in the opening, like this is science fiction stuff about how ML and humans can really collaborate together to produce a result. I always use in my mind, I always picture the metaphor, if anyone's seen the movie Avatar, of the soldiers and the exoskeleton, right? It's not that you have the human and the robot and they're like working side by side, but actually that the ML can provide a superpower, right? It can really amplify the skill of the agent, the skill of the human who has been trained in this client's annotation instructions. They know what the objects of interest are. They can go and seek them out within the context of an image in a real world environment. Say, hey, this is the one I care about. Let me drop my 4 extreme points, then do the handoff to the ML, right? And get a more accurate prediction back and really supercharge the ability. And the interesting thing about the level of the agent using these tools, I mean, we've been doing this for over a decade. We have, as I talked about, our social impact early on in the project. We specifically work with an impact population. Many of our of our agents grew up in the slums of Nairobi or in rural northern Africa, kind of survivors of the civil war there in the late 80s or early 90s. And we have a proven track record of saying, okay, we can take people who have this background with Sama's training program and the type of work that we do, and they can be very, very successful in terms of the dignified work and the social impact of the mission. And we haven't seen any drop off in that. There's nothing that has to do with using the ML integrated in the platform that has caused us to question anything about that mission or the social impact population that we've been working with.
Great. So we've got a question here from Mohammed asking, do you support video annotation?
Great question. So Mohammed, in terms of our data annotation capabilities, definitely support video annotation. I had a quick slide on early on, but basically it looks very much like our vector annotation interface, like I was just demoing. But the big difference there is then that wouldn't just be a static image, it would be sequential frames where we get the benefits of object tracking as well. So not just the same kind of object detection and localization annotation I was doing, but being able to say, okay, that's vehicle 1 and here's vehicle 1 in frame 1, frame 2, frame 3. Really helpful for path planning in particular, understanding how different objects trend over time. At this time, though, we do not currently support ML annotation within a video context. It's one of those things that in terms of the initial, or we made the initial investment in image annotation and then still need to extend it into video annotation. So as a manual annotation product, definitely answers yes. And in terms of integrating ML into that workflow, it's very much on the horizon.
Okay, and Sumit has asked if you can show an example of overlapping objects. Ooh, or perhaps
that's a good challenge. Let's see if I can go back into demo mode. I can't speak to the results, but I'm happy to. We'll do it live together and we'll see what the results are. Again, the model can be trained either way to kind of optimize for instance segmentation or semantic segmentation. So I'm actually not sure if your question was just seeing if it can kind of perform well when there is some occlusion. So let me do an instance one first. We'll see how the model performs. So pretty good. It has an awareness that it shouldn't include this whole vehicle. Let me even try to give it a little bit more information and see if we can. Yeah, there we go. Nice and tighter around that instance, even though it is occluded. And then let me try to do a semantic segmentation annotation. Let me just hide some things. Okay, so we'll try to get both of these objects in a single polygon now. And again, this performance here is not about what's necessarily, this is not going to be an example of what's a best case possible scenario, but only if the model was trained to behave in that way. So yeah, it's not bad, probably a little bit lower on the IOU, and then the agent could come in and refine that, but here's an example of it performing. Just tighten up on the mirrors here again across a semantic segmentation scenario. Hopefully that's what you were looking for.
Great, thank you for that. Okay, so we've got quite a few more questions here. So another one from Karthik asking, do we have to train again if there is a new product? How generic is your model?
Sure, yeah, and so the quick answer there is yes. Again, we're taking more of a micro-model approach here where we are doing custom training within specific contexts and specific annotation requirements. Though because they're lighter weight models, they require significantly less input. So typically within the first 1 or 2 weeks of a new engagement, we're able to train that model and have it deployed in production and then refine it further from there in terms of covering those use cases if it's something that we haven't seen before in terms of any of our core models.
Okay. Vikas has asked, how do parameters such as natural light, image resolution affect the quality of predictions?
Yeah, so those are definitely factors. As anyone has any experience training a computer vision model, right? Those are different factors that definitely introduce noise into the data and increase the challenge of the computer vision model to perform well in that variety of conditions. As I was highlighting within the one automotive use case that I was highlighting with one of our clients, we have experience with this in terms of continuing to feed more and more diverse scenarios into the data as they are getting annotated. And because of the micromodel approach, where that training loop is pretty tight, we can retrain and capture more of that data so that it will it will continue to perform well, even in those evolving conditions. So we might see a little bit of drop off on model performance when there's something totally new that gets introduced. Again, as I mentioned, we kind of have that instrumentation in place to identify where that model drop off is happening and therefore requiring more human intervention. So may see less efficiency during that initial blip, but then retrain, come back, and we can see the model performance tick back up.
Okay, great. We've got another question from Lumi who says, are there 3D representations of the models? In your example, is there a base 3D car somewhere being adjusted according to the human corrections in the annotation?
So I wouldn't call it a 3D representation of the model. As I was trying to show on the Dexter slide, what we're passing into the model is a heat map. So a heat zone within the larger image. So we're saying, hey, we're focusing on this specific area. We believe that there's an object of interest here. That is what gets fed into the model. And then the model will produce actually a raster mask is the first thing that it produces. And then there's a second piece of technology that we use to convert that back into a polygon that more closely simulates what a human would have drawn. So I don't know that it would be fair to say that there's a 3D representation at any point in that process.
Okay, and Tobiah has asked, are there some possibilities with 3D models over a 2D image? For pose estimation, is there a tool which lets me manually or semi-manually fit a 3D model over a 2D image to produce annotations?
Yeah, so not specifically in the technology that I was demoing today, but this is one of actually the research topics that we're looking at right now. We're seeing definitely an increase in the market in terms of sensor fusion use cases where we may have multiple 2D vantage points of the same scene, or certainly in combination with a point cloud or a LiDAR sensor. You can imagine a self-driving car use case where you have a LiDAR sensor mounted on the ego vehicle and then several 2D cameras. And there is some really interesting research that our team is looking in that looks at mapping between 3D and 2D space and using one to inform the other. And that is actually amplifying the model performance by feeding those two different pieces of having the 3D representation as well as the 2D imagery and how they interplay with one another.
Okay, great. And Rabindra has asked, in a real-time project, do we need to do manual polygon creation? How do we automate, take it to actual live data to predict? And how does the end-to-end workflow? Yeah,
so yes, there can be a role for manual polygon creation. As I mentioned, we have some experience with specific classes and use cases that kind of even on day one of a project, we may be able to launch already with the machine-assisted annotation and doing the predictions like I just demoed. And in some cases, there requires a little initial ramp up where the workflow would be 100% manual. The agents are creating that training data. We'll then feed that into the model to customize something to that specific use case. And again, maybe it's a week or two, then deploying the machine learning within that. And then that kicks off the secondary process, which is the iteration. Because once we have the ML live on the project, we are then also understanding when the agents are making significant modifications to those predictions and may even then do additional training cycles after that initial deployment.
Okay, and we have another question from Lumi asking, does a model need to be that specific to understand that the object is a car?
So that is, I think, need is the operative word there. We definitely observe the best performance using a targeted model that has been trained on a specific domain. What we observe is that the accuracy of these models is really critical to actually having the positive outcome that we observe. Even just a couple of percentage point slippage in that IOU metric in terms of the accuracy of the prediction can very quickly dilute the efficiency gains that we observe. And so by having that high accuracy of that prediction, the agent's spending minimal time manually modifying that. And that's where we really see the best gains. And the path that we've taken to doing that is these more targeted micromodels that we've been using to produce that high accuracy.
Okay, and we have a question moving away from this industry slightly that we've been talking about, asking what are the possible use cases of data annotation in the healthcare industry?
Yeah, totally. So within healthcare, we see, at least on Sama's side, we see a lot of use cases within the medical imagery space. That is a pretty expensive and pretty manual process currently in the market. So where there are opportunities to apply computer vision and machine learning to that problem, there's big opportunities there. And so we see a mix of MRI data as well as kind of X-rays or even surgical instruments. Those are all examples of use cases that we see in terms of being able to diagnose or interpret the medical imagery, as well as some like proactive monitoring of surgeries and things like that to help identify errors manual errors in surgery while they're occurring, are just a few of the examples. And then closely related to med tech, as I also mentioned, we're also seeing a lot of use cases in agro-tech as well, in terms of, specifically crop monitoring, irrigation, disease, pest control, and optimizing for the optimal outcomes in terms of yield for agriculture.
We have another mid-tech question from Sumit asking, can this be trained to annotate Acne vulgaris using bounding box, wherein 50 to 60 acne are present on the skin area?
Sure. So I think in terms of a use case, that sounds really, really interesting and makes a ton of sense. This model in particular is optimized for polygonal annotation and not specifically bounding boxes. There are a few other technologies that we've looked at. We don't have anything currently live in production in the bounding box space. But as I mentioned, one of the things that's really interesting about machine-assisted annotation is that it's not always a clear win, right, in terms of implementing machine learning in the human annotation process. Typically, bounding boxes, at least on Sama's platform, I didn't demo it, but we have this similar crosshair tool for bounding boxes. They're 2 clicks to draw. And so as opposed to polygonal annotation, where it's quite labor intensive to do a detailed contour around the object of interest, bounding boxes are relatively quick to draw. And so the amount of difference between the time it takes to drop 2 clicks to drop an accurate bounding box around an object of interest, and the amount of time it may take to audit and correct a pre-annotation or another ML approach for predicting bounding boxes, there's not quite that same delta in terms of opportunities for efficiency gains from ML, which has been one of the core reasons that we focused on polygonal annotation initially.
Okay, and we have a question about, does Sama have any intent on entering the image manipulation area in the movie industry? A different industry again.
Yes. So we haven't seen as much of that use case historically, though it's from a product perspective, actually, video editing and manipulation software is one of the different tools that we look at for inspiration when thinking about what do we want our annotation interface to look like and how are we presenting that to our agents to enable that efficient annotation. And there actually has been a ton of innovation in the video editing space that then is kind of downstream informing innovations in the data labeling space as well. So it's not something that we've explored very seriously historically in terms of the demand for our products and services, but certainly something we're aware of.
Okay, and we have a couple more questions. One question asking, are there any NLP solutions?
So I wonder if it's any of the Sama people on the line who put that question in, because it's good timing. Check out our blog. We just launched our NLP product, I think last week, I want to say. It's something that we have done in a limited capacity for over 10 years now. And Sama platform that I demoed had always had the ability, in addition to the computer vision outputs that I was talking about, the vector image annotation and the raster annotation and the video annotation, had always had the ability to also work with text and classifying that text. And of course, all that's happening within the larger context of the Sama platform, which is much more than just the annotation workspace, but really thinks about what is a scalable, highly available platform to drive your data annotation workflow. Everything from queue management and how tasks get assigned to qualified agents, to quality management, workflows, reporting, and obviously the API integration. So like the annotation workspace is actually it's a small part of a much larger platform that's required for doing these kind of data annotation projects at scale. However, we recently just made big investments in terms of some of the specific features that are really powerful for NLP use cases, like name entity recognition or parts of speech, as well as what we see much more in the NLP environment is multiple submission-based approaches and the quality management features that go along with that in terms of measuring interagent agreement and things like that. So I'll just kind of not talking about it on this call, but kind of put you to the SAMA blog. There's a recent post on our NLP offering and some brand new pages on our website that it's been an exciting time.
Okay, great. Well, we can share those links in the email along with this recording for anybody that's interested. And we have a question from John asking, how can SAMA still ensure high quality annotations with the introduction of ML? Yeah,
absolutely. So, I mean, as I was talking about, the human element of this kind of work can't be understated, right? And so everything that I'm demoing, right, I was in the agent workspace. The human is a co-creator in that polygon annotation and is responsible for auditing and refining it to make sure that it meets the high quality bar. And so in many ways, we would argue that the quality hasn't changed, right? You're still getting that value of that skilled agent. It's just, what's the path to getting there? The path now has ML as part of that workflow with that human in the loop, still resulting in the same high quality annotations.
Okay, and we have one final question, unless we get any last minute ones. How is machine assisted annotation different than pre-annotation?
Great question. And actually, so yeah, Nikita, I'll work with you to include the link to the research paper that I referenced earlier in the email as well, because it's a really fascinating topic. So what we observed is, as I've kind of hinted on a few times, and as you saw in the demo, right, that it's the user who is helping identify the object of interest and also defining its boundaries and passing that as an input to the prediction model. So that does a couple of really interesting things. One, in a pre-annotation context, it means that when the agent would open the workspace, the model has already made decisions about what are the objects of interest, where are they, what are their extreme boundaries, and at that point purely puts the user in the role of kind of auditor and corrector, right? So that's more of the, as I mentioned, kind of like the robot and the human kind of side by side, right? Where the robot's doing its thing and the human's doing its thing. Whereas what I was demoing there with machine assisted annotation, where it's integrated into the workflow, first, it kicks off with a user input. And so I would say that that's more like the exoskeleton metaphor from Avatar, like I was talking about before, where it's actually the human working in combination with ML simultaneously and co-creating. And as I mentioned, I'm kind of teasing it in that research paper, we did see a big difference between those two scenarios. It may sound at face value very similar, but it actually makes a huge difference to involve the human in that creation process in terms of how it results in and actually drives down the editing time required to produce the same end result.
Okay, and just we've had one more, so we'll close up after this one. Lumi has asked, where is the feature of computer vision and machine learning? Quite a big question. And linked to that, as a visual effects profession looking into computer vision and machine learning, what specific part of this large field would you suggest?
Yeah, so I think, I have to like, these are big questions for sure. So I think that where I would say what we're looking at right now is I covered a lot of those industries and use cases, but I do still think that the barriers to computer vision are quite high. I think, first of all, we're just all starting to appreciate the real world applications and the disruption that this technology can play in a variety of use cases. And so one of the things that I get so excited about with the machine assisted annotation, as I think I mentioned earlier in the call, is driving down that time and effort that it takes to produce these high quality annotations that then result in the high performing models. And so again, many of the logos we work with are some of the biggest companies, most innovative companies in the world, which are valued partners of ours, but also like how do more people who have ideas get started, right? And how can we drive down that barrier? Because if the barriers to entry are reduced, then all of a sudden this becomes a much more viable, computer vision in general becomes a much more viable solution to a much larger ranges of problems. And it's not just the commercial ones. We have a well-documented long-term partnership with the Paul Allen Foundation and Vulcan, actually using computer vision to identify elephants in the wild and help drive down poaching, right? So as much as typically when we come into these conversations, yeah, we're talking about self-driving cars and we're talking about AR, VR or filters and in smartphones, like there are a variety of applications that may not have the same kind of commercial upside that is currently fueling the R&D effort. And we're on Sama's side, we're really supportive of seeing more of that.
Great. Well, thank you so much, Saul, for taking the time to answer quite a few questions and for the presentation and the demo as well today. So as I said, we will share the recording with everybody after this, along with links to papers and blogs that you've spoken about as well, so that everybody can have a chance to look at them in their own time again. And also we'll just share some contact details if anybody wants to ask you any more questions. And thank you again to Sama for hosting the webinar with us today. It's been great to have you involved again.
Yeah, Nikita, thanks so much for having me. And thanks to everyone for joining and the thoughtful questions.